there are certain battery parameters that you should be aware of in order to select and specify for batteries. One of the most important parameters is capacity of the battery. What is capacity of the battery? So let us consider this figure which gives you a picture of the battery symbol, and these are the battery terminals, let us say, and then there is a current flowing into the battery positive terminal, and that is called IB, and let me mark the voltage across the terminals and we'll name it as VB. Now, given such a battery with the terminal voltage VB and the current flowing into the battery positive IB, which means is the charging current, we can define the capacity, the energy capacity, in the following manner. So you have integral VB IB dt. This is nothing but energy in watt hours, and IB, if it is positive, IB is positive means it is flowing into the positive terminal, meaning it is charging the battery. So this implies charging. Then the energy that you would calculate in this fashion would be the charging energy, E charge. On the other hand, if IB is negative, meaning IB is flowing out of the positive terminal, it is flowing in the reverse direction as indicated here, then it implies that the battery is discharging. Then the energy is representing the discharge energy, E discharge. Therefore, when you say capacity of the battery, it would mean the watt hour capacity, how much amount of energy that the battery can hold, how much amount of energy the battery can discharge to the load. So we talk in terms of watt hours. However, you can also talk of the capacity in terms of charge, Coulombic charge. Integral of IB dt is nothing but is C, and it is nothing but ampere hour. Ampere hour is nothing but the charge. So it's the charge capacity. So people use this definition also to indicate the capacity of the battery. Now that, if you compare these two, if I have VB constant, then you will get the ampere hour capacity. So watt hour capacity or the energy capacity is the true capacity of the battery. It will give you the true capacity, energy, watt hour capacity of the battery. However, if VB is constant, if VB is maintained constant here, then integral of IB dt, C, the ampere hour capacity, will be a direct measure of integral of VIB dt, that is the energy capacity. Then the charge capacity, C, or the ampere hour capacity, will give you a direct measure of the watt hour of the battery. In the commercial world, this ampere hour capacity, as defined here, integral of IB dot dt is equal to C ampere hours unit. Now this charge capacity is the one which is more popular, and you will see that in almost all the battery specs, and people using the AH of the battery, the AH spec of the battery much more commonly than WH spec of the battery. So therefore, when you look at battery data sheets, the AH of the battery is a much more common battery capacity spec than WH. So commercial usage terms, this is much more commonly used. Consider the figure of the battery as shown here. You have the positive terminal, negative terminal. Let us take the analogy of a water tank. In the case of the water tank, when you have the water tank full of water and you say the tank is full, likewise, even in the case of the battery, when it is fully charged, you say it is full. And under full charge condition, the open circuit voltage across the terminals will be maximum. Take for example, in the case of a lead acid battery, a 12 volt lead acid battery which you would find being used in cars and vehicles, you will find that it is around 14.3 volts, not actually 12 volts but 14.3 volts under full charge condition. Now consider another level, a level X. Now at this level, the amount of charge available is much lesser than full tank, and like in the case of the water tank, once the water level has decreased to level X, the potential is also reduced. Same way here also at level X, the voltage across the terminals of the battery is much lesser than the voltage that you would find across the terminals when the battery is full. Suppose if the battery is discharged to the level X, then the depth to which it has discharged is called DOD, the depth of discharge. So from 100% to X%, so 100 minus X% is called the depth of discharge, depth from full. So it is called the depth of discharge and normally expressed as percentage, and it's a very important specification parameter that you will see in battery specs, and it has a lot of influence on the life of the battery. We will discuss that shortly. So when you say the battery has gone from full tank to this level X, this much amount of charge as shown shaded here is the amount that has been utilized. So this is the utilized charge, and if you set X as the limit, that you don't want the charge level in the battery to go below this, because you would like to have minimum potential and maximum potential limits, and if you don't want the potential across the terminals to go below a particular level, so let's say you would decide on a lower limit of the charge level for the battery, just like you define a lower limit of the water level for the water tank. So then this shaded area would become the usable charge or the usable capacity of the battery. So this level is corresponding to the usable watt hour or ampere hour of the battery. DOD is measured from full to the level X. Just like you measure from 100% to the level X, you can measure from 0% to the level X to get the state of charge. So if I measure from 0 to a level X as shown here, then you call it as state of charge. State of charge is nothing but 100% minus DOD percentage, and that is equal to 1 minus DOD by 100 into 100, state of charge being expressed as percentage. So DOD and state of charge are complementary. State of charge will give you the amount of charge existing in the battery. DOD, depth of charge, will give you the amount of charge or the watt hour that can be used up or has been used to supply to the load. State of charge is also expressed in percent. So at an arbitrary level x, let us say the battery voltage is x, VBx. Note that VBx will be less than the battery potential at full capacity or full charge. So as the charge decreases, the battery terminal potential also decreases. You can set a voltage below which you do not want the battery to discharge, and that would be the limiting voltage or the fully discharged condition voltage as far as your application is concerned. So for example, in the lead acid batteries, 12 volt lead acid battery, we will set it as 10.8 volts as the discharged condition, and we will not allow it to go beyond that, below that. So the voltage range for a 12 volt lead acid battery for most of the applications would be from 10.8 volt minimum to 14.3 volt maximum. Connected with this capacity and depth of discharge is life. Life of the battery. Life of the battery is expressed in terms of number of charge discharge cycles. One of the significant parameters this life of the battery is dependent on is the DOD of the battery, the depth of discharge of the battery. So the life depends significantly on the depth of discharge. As the depth of discharge increases, the life decreases. What it basically means is that if the depth of discharge is 20%, you have some number of charge discharge cycles. Let us say 1000 charge discharge cycles. If the depth of discharge goes down to 60%, this goes down deeper, that is, you are going into deep discharge, then the life would probably, let us say, come down to 200 cycles instead of 1000. So there is a kind of an exponential kind of a decay in the life as the depth of discharge for the battery increases. So DOD is an important parameter in determining the life of the battery.